We live in a world of movement. To make it all possible, we need energy. In fact, energy is needed for everything we do. Today, our demand for energy is enormous. A lot of it comes from power stations dotted about all over the country. The energy they supply is carried by electricity along wires, so it's easy to distribute. But a power station does not produce energy. Instead, it has the job of transferring it from something else, and that's usually coal. Coal is one of our most important sources of energy. Oil is another. But we know that supplies of coal and oil won't last forever. If we let these supplies run out without doing anything about it, you could probably guess what will happen. Everything will stop. Everything, that is, except the sun. That should continue to pour out energy for some time yet. The only problem is collecting it. One solution is found in nature. As sunlight falls onto the green leaves of plants, they store energy from the sun. It's the way a plant makes food. Here, the world's fastest growing plant is being harvested by scientists who found a possible way of using the plant to provide us with energy. The plant is called the water hyacinth. In the laboratory, the fully grown plants are chopped up and put in a container where they'll be left to rot. In 13 weeks' time, the rotting plants will produce a gas called methane. It burns with a colorless flame. But using water hyacinth as a source of energy on a big scale would need a lot of space. For example, to provide the energy we use in England, we'd need to grow the plants over an area as big as England itself, plus Scotland as well. On that scale, it's hardly a good idea. But what about doing it on a much smaller scale? People with gardens could give part of them up for growing these plants. Then, if a special processor was built at the end of the street, it could be fed with plants from the neighborhood. It's only an idea, but it would at least provide some energy, saving supplies of coal and oil. Energy collected from the sun. But there are other ways of collecting the sun's energy. On the roofs of these houses in London are glass-covered panels designed to collect heat from the sun. They've been put on the roofs as part of a carefully controlled scientific experiment. Each of the glass panels, or solar collectors as they're called, contains a series of pipes running up and down. The pipes are part of a circuit containing a liquid that's pumped from the bottom to the top. Heat from the sun causes the liquid to warm up. At the top of the panel, the warm liquid flows out through a pipe connected to a water tank beneath. There, it warms the water inside. In the tank, the liquid flows through a coiled tube. The colored dots mark the positions of measuring instruments used to monitor what's happening. Beside the tank is the pump, keeping the liquid circulating through the solar collector. As the warm liquid flows down from the collector, its temperature is measured. The sun's energy can get the water hot enough for washing up. To get it hotter, there's also an electric heater, and a measure is being kept on just how much electricity it's using. On the roof, more measurements are being taken. First, there's the speed of the wind blowing across the panels. Then there are measurements on the amount of sunshine falling on them and how strong the sunshine is. All these measurements are fed straight into a computer. From the results, scientists hope to discover how this idea of collecting and using the sun's energy might be improved, simply and cheaply. It's an idea that's certainly catching on. These houses are in Milton Keynes, and they've not long been built. They've all been specially designed with roofs that are big solar panels. But these solar panels only form the roof on one side of the houses, the side that faces south. Over the road, the roofs face north and are covered in tiles. On this side, the houses have been designed with their solar panels at the back. On the south-facing roofs, it's all because in this country, the sun is in the south. So as well as growing plants to collect the sun's energy, we could also have solar panels on our roofs, a sort of energy-collecting neighborhood. But it needn't stop at that. As the sun heats up the air, it causes the air to move, and the energy of moving air is something we've been collecting for centuries. Old windmills like this one have specially shaped sails designed to catch as much wind as possible. To keep the sails in the wind, there's a device called a fantail. As the wind changes direction, the fantail turns the mill back into the wind. The turning sails are mounted on a shaft. Inside, gears, often made of wood, speed up and transfer the movement from one direction to another before finally turning the millstones. These old mills were built by craftsmen using the best materials to hand and all the scientific know-how they had. With new materials and more scientific know-how, we're able to build more efficient windmills today. This one is designed to generate electricity. The sails, or blades, still need to be kept in the wind, and the old method of using a fantail is still found to be one of the best. This windmill, or wind turbine as it's called, is under test. In front of the turning blades is a tower carrying an array of instruments measuring the energy of the moving air. Behind, there's another tower of similar instruments. Readings from these help scientists to discover how much energy the wind turbine is collecting. The measurements are recorded continuously in a nearby hut with the help of a computer. Two of the most important measurements are wind speed and wind direction. The scientist can get an instant readout of all the measurements being taken on a visual display screen. Among these readings are measurements on the blades, on the enormous forces acting on the blades. This turbine is designed to generate enough electricity to heat up about 100 small electric fires. It's only a small amount of energy from a fairly large machine, but it's enough to make it worthwhile selling to the public electricity supply. To collect more energy from the wind, you'd need to build a much bigger turbine than this one. Another idea is to build an array of lots of large turbines in one particularly windy area. That's an idea that's being tested out here at the Central Electricity Research Laboratories near London. It's an experiment being done on a miniature scale. Inside the wind tunnel is an array of mini windmills. In fact, they're special measuring instruments. They're being lined up to face the wind and will be used to measure the amount of energy the wind is carrying. When the wind blows, blades inside turn. The faster they go, the more energy they're collecting. Now for the test. Large fans at one end of the tunnel draw air through it, causing the little windmills to turn. They've been arranged one behind each other in the direction of the wind because what the scientist wants to know is how this arrangement affects the amount of energy each one collects. Once the fans have reached a constant speed, readings are taken from each windmill in turn. A record of the readings is typed out automatically. But these readings are only for one particular arrangement of the windmills. By turning the whole array on a turntable, the arrangement can be changed. The little windmills are no longer in line, one behind the other. Before repeating the test, they must now be turned into the direction of the wind. For each test, the wind tunnel fans are run at exactly the same speed. It's part of the scientific control. From these tests, scientists can discover if there's any one arrangement that will collect more energy from the wind than any other. On a test site outdoors, work is going on to assemble a group of large-scale wind turbines to check the results from the wind tunnel. The ones they're assembling are a new kind of design. They're made up of 3 fiberglass blades hinged at their centers to 3 spokes of a wheel. The blades are connected to each other by wires and have been molded into a special shape. As the wind blows over the blades, the turbine turns. The stronger the wind, the faster it goes. But as it gathers speed, the blades splay out. This has the effect of preventing the turbines from going too fast. Too much speed could damage the turbine. This kind of design has one great advantage. The blades don't have to be turned into the wind, so it doesn't need a fantail. In a moderate wind, these turbines spin at quite a speed, but it's not fast enough for an electrical generator. To speed up the movement, each turbine is connected to its generator through a gearbox. At the moment, the energy collected is being stored in accumulators, but they will supply enough energy for about 140 electric fires. These turbines are a new design. Here's a model of another. In this design, there are only 2 spokes to the wheel. The blades are made in 2 parts and joined together by a hinge. At fast speeds, the blades are shaped like sharp arrows, but at slower speeds, they open out. Again, it's a way of controlling the speed of the turbine. The faster it tries to go, the more the blades close up. This stops it running too fast. A modern turbine like this could be used in our energy neighborhood. With plants, solar panels, and now wind turbines, we could collect enough energy to supply the needs of a group of homes. And if there was any to spare, we could sell it to the public electricity supply, a sort of neighborhood power station. If for some reason the neighborhood was unable to collect sufficient energy for itself, it could always buy in supplies from one of the main power stations. Some of these might continue to transfer energy from coal or oil, or perhaps from nuclear fuel, although not everyone likes the idea of that. Our power stations of the future might even collect their energy from the wind using hundreds of enormous turbines in windy areas, probably out at sea. There are a number of possible sites just off the coast, and not only on the west side of Britain. On the east side as well. And we probably wouldn't only use turbines to collect the energy of the wind. As it blows across the surface of the sea, some of the energy is transferred to the water, producing waves. Waves carry energy, and scientists and technologists use special wave tanks to find out how to collect it. The waves are produced by moving paddles, controlled, would you believe, by a computer. The idea is to collect the energy in the simplest, cheapest, and most reliable way. That's the problem. There are many ways to solve it. One of the ways being tried out here is to use a raft-like device. As the waves hit the raft, it begins to rock, gently, up and down. The front half of the raft is joined to the back half by a hinge. This rocking movement could be used to operate a pump, forcing water through a pipe. The moving water could then be used to drive a water turbine. Another idea is to enclose a volume of air just above the surface of the water in a kind of box. In the top of the box there's a hole to let the air in or out. As the waves arrive, the water level inside rises and falls, pumping the air in and out of the box. From here, you can just see the hole through which the air is moving. If we now place a special wind turbine in the path of the moving air, we've got what it needs to drive an electric generator. Here, in another much larger wave tank, scientists are testing yet another idea. Just beneath the surface of the water are a series of hollow cylinders held there by chains. As the waves roll over them, they cause the cylinders to move, pulling on the chains holding them in position. In this test, the chains are fed round a pulley fixed to the bottom of the tank. The other ends are connected to measuring instruments on the surface. Again, this movement could be used to pump water for a water turbine. And yet another idea. It's a line of air-filled flexible bags sandwiched between hinged plates and a solid box-like spine. The waves squeeze the air in and out of the bags to turn a turbine. Here's a simple version of that design being tested in a smaller wave tank. No longer is there a plate in front of the airbag. That would make the device cheaper to make and easier to maintain. But does it work?
Waves on.
But remember, these devices to provide all the energy we need in Britain, we'd need a chain of these as long as the London to Glasgow motorway, probably sited around the northwest coast of Scotland. There are other places where they could be moored, off the southwest coast of England and the northeast coast of Scotland. If you live near the sea, you could use the waves along with the green plants, solar panels, and wind turbines to collect your own energy. Who knows, in the future, we may all live in energy neighborhoods like this.